The lighting systems of the 1800s that shouldn't exist, yet they're everywhere. When you walk the streets of historic European or American cities, you often encounter ornate cast iron lampposts that seem to belong to the Victorian era. Many assume these are modern replicas installed for aesthetic reasons. Surprisingly, a significant number of these lighting systems are original 19th century fixtures, still functioning through underground infrastructure that has remained operational for over 150 years. Even more remarkable is the engineering sophistication behind these systems, which incorporated principles of power distribution, automated control, and operational efficiency that anticipated 20th century developments. This itinerary will explore gas lighting systems, electric arc lighting, and hybrid systems that combined multiple technologies, revealing how 19th century engineers solved complex technical challenges with limited resources. We will examine coal gas distribution networks that stretch for miles beneath cities, mechanical timing systems that automatically switch lamps on and off, electrical generation technologies that powered arc lights bright enough to illuminate entire avenues, and innovations in lamp design that maximized luminous efficiency. Through analysis of historical patents, period technical manuals, and examination of still existing systems, we will reveal the often underestimated sophistication of Victorian engines. We will begin with gas lighting, which preceded electricity and established fundamental urban infrastructure. Coal gas, also called town gas or illuminating gas, was produced through the destructive distillation of coal in facilities called gasworks or gas plants. The process involved heating coal in sealed retorts in the absence of air, breaking down complex hydrocarbon molecules into lighter gases. The resulting gas was primarily a mixture of hydrogen, methane, carbon monoxide, and other volatile hydrocarbons. After production, the gas needed to be purified to remove impurities such as tar, ammonia, and sulfur compounds that were corrosive and reduced light quality. Purification involved passing the gas through a series of scrubbers, condensers, and filters. Tar was collected as a valuable byproduct, used in waterproofing and later in the chemical industry. Ammonia was captured and sold for use in fertilizers. Sulfur was removed using hydrated iron oxide in purification tanks. After purification, gas was stored in gasometers, massive cylindrical structures that could hold millions of cubic feet of gas. Gasometers operated on a telescopic principle, with sections that rose and fell based on gas pressure, maintaining constant pressure in the distribution network independent of varying demand. Some of these gasometers still exist as preserved structures in European cities. Gas distribution throughout the city was via a complex network of cast iron pipes buried beneath streets. Main pipelines were of large diameter, branching into smaller pipes that served individual streets, and finally into service pipes that connected to lighting poles or buildings. The system required constant maintenance because pipe joints were sealed with hemp rope and molten lead, a method that could lead to leaks. Engineers developed leak detection techniques, including the use of open flames moved along streets to identify locations where gas was escaping, a dangerous but effective method. Gas lamps themselves evolved significantly throughout the 19th century. Early lamps were simply open flames burning gas, producing weak, flickering yellow light. A crucial innovation came with the invention of the argon burner, which introduced airflow through the center of the flame, creating more complete combustion and brighter light. A more significant development was the introduction of the incandescent gas mantle by Karl Auer von Welsbach in 1890. The mantle was a mesh structure soaked in rare earth oxides that, when heated by the gas flame, glowed intensely, producing bright white light far more efficiently than an open flame. Welsbach's mantles transformed gas lighting, making it competitive with early electric lighting in efficiency and light quality. Automation was a notable feature of urban gas lighting systems. Engineers developed complex clockwork mechanisms that controlled valves at central points in the gas network, allowing streetlights to be switched on and off simultaneously at program times. Some systems used weight-driven clocks that needed to be rewound daily, while others used pneumatic or hydraulic mechanisms. In London, a particularly sophisticated system used a master clock that sent pressure pulses through water pipes to activate valves throughout the city, synchronizing street lighting with remarkable precision for the pre-electronic era. Lamplighters, workers who roamed the streets lighting lamps individually with long poles, are romanticized in literature, but they represented only a transitional period before automation became standard. If you're fascinated by sophisticated historical engineering that anticipated modern technologies, leave a like now. Subscribe to the channel and activate the bell for more in-depth analysis of forgotten innovations. And if you want to support this work of bringing verifiable facts about the history of technology, click the Hypar button below. Your support allows us to continue producing rigorous content. Now let's explore electric arc lighting. Electric arc lighting, intense brightness. Before the incandescent lamp. Before Thomas Edison commercialized the incandescent light bulb in 1880, electric lighting already existed in the form of arc lamps, a technology developed in the early 19th century, but which only became practical for public lighting in the 1870s and 1880s. An arc lamp produces light through an electrical discharge between two carbon electrodes. When an electric current passes through the small airspace between the electrodes, the air ionizes and becomes conductive, creating a bright electric arc that emits intense light and tremendous heat. The temperature in the arc can exceed 3,000 degrees Celsius, gradually vaporizing the carbon electrodes and requiring constant adjustment of the distance between them. The principle was discovered by Humphrey Davy in 1807, but limitations in electrical power sources prevented practical application for decades. The development of efficient electric generators, particularly Graham dynamos and Siemens dynamos in the 1870s, made it possible to supply the constant current necessary for operating arc lamps. The main technical challenge was maintaining the correct distance between electrodes as carbon was consumed. If electrodes were too far apart, the arc would extinguish. If too close, they would short circuit. Inventors developed ingenious regulating mechanisms using solenoids, springs, and gears to automatically advance electrodes as they wore down. The most successful regulator was developed by Charles Brush in the United States, whose system used an electromagnetic clutch to control electrode advance with remarkable precision. Brush's arc lamps were installed in multiple American cities beginning in the late 1870s. Arc lamp brightness was extraordinary compared to any previous artificial light source. A single arc lamp could illuminate an area equivalent to dozens of gas lamps, making it ideal for lighting large spaces such as main streets, public squares, docks, and railway stations. However, the light was too intense for indoor use in homes or offices, limiting applications to outdoor and industrial lighting. The color of the light was also a problem. Arc lamps produce bluish-white light with a continuous spectrum, but deficient in red wavelengths, giving people a cadaverous and unnatural appearance. The installation of arc lighting systems required significant infrastructure. Generating stations needed to be built to house dynamos driven by steam engines. Copper electrical cables needed to be installed to distribute power to the lamps. Unlike gas, which could be stored in gasometers, electricity needed to be generated continuously during operating hours. Early systems used series circuits, where multiple arc lamps were connected in a single line, with current passing through each lamp sequentially. This meant that if one lamp failed, the entire circuit would be interrupted, extinguishing all the lamps. Engineers developed automatic cutoff devices that bypassed failed lamps, but series systems remained vulnerable. Transition to parallel circuits, where each lamp had an independent connection to the power source, improved reliability but required higher voltages and more careful insulation. Arc lighting towers were a distinctive feature of some cities. Instead of lamps mounted on street-level poles, enormous metal towers, some over 60 meters high, were built with multiple arc lamps mounted on top. The theory was that elevated lamps could illuminate a larger area, similar to an artificial moon. Cities like Detroit, San Jose, and Denver installed tower lighting systems in the 1880s. Although visually impressive, they proved problematic. Harsh shadows created extreme contrast, maintenance required dangerous climbing, and strong winds could sway towers and damage equipment. Most tower systems were abandoned in favor of conventional pole-mounted lamps. Notable aspect of arc lamps was sound. The electric arc produced a characteristic hum and occasionally a hiss or crackling sound as the arc's position shifted between electrodes. On calm nights, this sound could be heard from a considerable distance, adding an auditory dimension to the electric lighting experience that was completely different from silent gas lamps. Hybrid systems and coexistence of technologies. During the late 19th and early 20th centuries, it was not uncommon for cities to operate both gas and electric lighting systems simultaneously, and some streetlights were equipped with both technology. This coexistence reflected gradual transition, differing reliability of each system, and specialized applications for which each technology was better suited. Hybrid streetlights, equipped with an electric arc lamp at the top and a gas lamp below, were a practical solution for providing backup if the electrical system failed due to a problem with the generator or distribution network. Gas lamps could be lit to maintain basic lighting. Conversely, during periods of high demand or gas system maintenance, electricity could compensate. This redundancy was particularly valued in critical areas such as central business districts, hospitals, and government facilities. Period documentation shows that some cities maintained this dual approach for decades until electricity reliability improved and it became economically unfeasible to maintain two separate systems. Another aspect of coexistence was the division of applications. Electric arc lighting was preferred for main streets, squares, and areas requiring intense illumination. Gas lighting remained dominant in smaller residential streets, parks, and areas where softer light was sufficient and preferable. Building interiors often used gas due to lower cost and ease of installing multiple light points. The transition to incandescent electric lighting, which began to accelerate after 1880, added a third layer of complexity. Incandescent lamps offered stable, soft, easily controllable light that was superior to both gas and arc lamps for indoor lighting. However, they required different low-voltage electrical distribution infrastructure than that used for high-voltage arc lamps. Engineers developed separate generation and distribution systems, low-voltage direct current for indoor incandescent lighting, and high-voltage direct or alternating current for outdoor arc lighting. The battle between direct current, DC, and alternating current, AC, for electrical distribution had significant implications for lighting. Thomas Edison advocated for DC, arguing that it was safer and better for incandescent lamps. George Westinghouse and Nikola Tesla promoted AC, which could be efficiently transmitted over long distances using transformers. For arc lighting, both DC and AC worked, although arc characteristics differed. AC produced a more stable and quieter arc, while DC consumed electrodes more evenly. Eventually, AC prevailed for power distribution due to transmission advantages, but the transition took decades, and many cities operated DC and AC systems side by side. Distribution engineering, complex underground networks, underground infrastructure needed to support gas and electric lighting was a massive engineering undertaking that transformed the urban landscape. Gas pipelines and electrical cables needed to be installed beneath streets without excessively disrupting traffic, protected from moisture and mechanical damage, and kept accessible for repair. Solutions developed in the 19th century laid the foundations for modern utility infrastructure. For gas, trench excavation was the primary installation method. Trenches were dug along streets. Cast iron pipes were laid and connected with lead joints, then covered. Installation depth needed to be sufficient to protect pipelines from freezing in cold climates and from damage from surface traffic. Typically 1 to 2 meters. Pipelines were tested for leaks using air or water pressure before being put into service. Maintaining gas networks was an ongoing challenge. Leaks were common due to corrosion, soil settlement, and traffic vibration. Leak detection evolved from primitive methods such as listening for hissing or smelling gas to more sophisticated techniques using portable fuel detectors by the end of the century. Repairs often required excavation and replacement of pipe sections. Disruptive work that could block streets for days. Electrical cable installation presented different challenges. Early overhead systems, with cables hanging from poles, were relatively simple to install, but vulnerable to weather and considered unsightly. The move to underground cabling began in major cities in the 1880s. Cables needed to be insulated with rubber, gutta percha, or oil-impregnated paper to prevent short circuits due to moisture. Multiple cables were often bundled in conduits. Protective metal or concrete tubes that provided mechanical protection and facilitated cable replacement without total excavation. New York City pioneered an elaborate underground conduit system where large junction boxes were built at intervals along streets, with conduits connecting them. This created a network of underground passages through which cables could be pulled and where splices and connections were made. Access was through cast iron covers at street level, familiar even today. The conduit system allowed for the expansion and modification of the electrical network without the need for extensive excavation each time changes were required. Engineers also developed techniques for routing gas pipes and electrical cables together in utilidors, underground corridors that contained multiple utilities. This simplified maintenance by providing direct access, but required careful ventilation to prevent gas buildup and separation of electrical cables from gas pipes to minimize the risk of ignition. London built some of the most extensive utility-door systems during Victorian infrastructure expansion. Control and automation, clocks, timers, and valves. Public street lighting automation was a priority for municipal engineers, both for operational convenience and to reduce labor costs. Systems developed in the 19th century to automatically turn lamps on and off were remarkably sophisticated, using mechanical, pneumatic, and hydraulic principles. For gas lighting, the simplest method of automation was a timer valve installed at a central point in the network, controlled by a clockwork mechanism. The clock was set to open the valve at dusk and close it at dawn, with seasonal adjustments made manually to accommodate changes in daylight hours. Clocks were driven by weights or springs that needed to be rewound regularly, a task performed by gasworks operators. The accuracy of these clocks was limited, with deviations of a few minutes per day being common, but for street lighting this was acceptable. More advanced systems used a master clock that controlled multiple valves through mechanical or pneumatic transmission. In Paris, a system installed in the 1860s used a series of rods and levers connecting a central clock to valves in different parts of the gas network. Clockwise rotation moved rods, which in turn opened or closed valves. Although ingenious, the system was limited by friction and mechanical flexibility, functioning only over relatively short distances. London developed a particularly elegant solution using a network of pressurized water pipes separate from the gas network. A master clock in a central installation opened and closed a valve in the water pipe, creating a pressure pulse that propagated through the network. At each lamppost or group of lampposts, a pressure-sensitive device detected the pulse and activated a local gas valve, turning the lamp on or off. The system allowed centralized control of thousands of lamps, distributed over a vast area without the need for electrical wiring or complex mechanical. Maintenance required only ensuring that the water network remained pressurized and that individual pressure sensors were functioning. For electric lighting, automation was more straightforward in some respects, but presented unique challenges. Electric generators and power stations could be switched on and off according to a schedule, and time switches could control individual circuits. However, arc lamps required constant electrode adjustment during operation, and arc starting required a higher initial current. Systems used time relays, solenoids, and mercury switches to sequence startup and shutdown. Some systems incorporated light sensors, primitive photoelectric devices using selenium cells that changed resistance based on incident light. These could automatically turn on lamps when ambient light fell below a certain level, providing responsive automation rather than just time-based automation. Although selenium cells were expensive and not entirely reliable, they represented a step towards adaptive control. Efficiency and economy, operational costs, and energy consumption. Public lighting was a significant municipal expense, and the efficiency of different lighting technologies was constantly evaluated by city administrators. Cost comparisons considered not only energy or fuel expenditure, but also infrastructure installation, maintenance, equipment durability, and labor costs. For gas lighting, costs included gas production in gasworks, maintenance of the distribution network, and operation of lamps. Gas production required coal, which needed to be purchased, transported, and stored. Labor was needed to load coal into retorts, remove ash and tar, and operate purification equipment. Maintenance costs included repairing leaks in pipelines, replacing gas mantles as they wore out, and cleaning burners. The labor of lamplighters when used was an additional cost. Byproducts of gas production, including coal tar, ammonia, and coke, could be sold, partially offsetting costs. Coal tar became particularly valuable with the development of the chemical dye industry in the late 19th century. The luminous efficiency of gas lamps improved dramatically with the introduction of Welsbach mantle. An open flame lamp produced about 0.2 to 0.3 lumens per watt equivalent of gas energy. A Welsbach mantle lamp produced 1 to 2 lumens per watt, of 5 to 10 times. Improvement. This made gas lighting competitive with early incandescent electric lamps, which produced 1.5 to 2.5 lumens per watt. For arc lighting, costs included electricity generation, maintenance of generators and steam engines, distribution through the electrical grid, and replacement of carbon electrodes in lamps. Generators needed to be operated continuously during lighting hours, consuming coal or other fuel to power steam engines. Generation efficiency was low by modern standards, typically 50% to 60%, meaning that half the fuel energy was lost as heat. Arc lamps were more efficient than gas at converting energy into light, producing 5 to 10 lumens per watt. But intense brightness meant that light was often wasted, illuminating areas far beyond what was needed. Carbon electrodes in arc lamps were consumed at a rate of a few centimeters per hour, requiring frequent replacement. Depending on the lamp design, this could be a daily or weekly task. Electrodes were relatively expensive, and replacement labor added to operating costs. Incandescent electric lamps, when they became available, offered lower efficiency than arc lamps, 1.5 to 4 lumens per watt depending on the design, but were much more convenient, required no adjustment, and produced soft light suitable for more application. Infrastructure installation costs initially favored gas, because many cities already had established gas networks, while electrical infrastructure needed to be built from scratch. However, once electricity became common for uses other than lighting, particularly for electric motors in industry, economies of scale favored the expansion of electrical grids. Innovations in lamp design. The physical design of lamps evolved significantly, driven by efficiency, durability, aesthetics, and maintenance. Lamps needed to withstand harsh weather, provide adequate light, and be accessible for repair. Early gas lanterns were glass boxes with burners suspended from iron supports. Innovations included heat-resistant borosilicate glass, designs promoting air circulation to prevent soot, and reflectors directing light downwards. Fresnel lenses were adapted to focus light efficiently. Materials for lamp posts were cast iron, chosen for durability and ability to be molded into decorative shapes. Ornate designs reflected Victorian values with lampposts featuring floral motifs and municipal emblems. Design complexity added structural rigidity. For electric arc lamps, enclosures protected the regulating mechanism while allowing ventilation to dissipate heat. Frosted glass globes diffused bright light and reduced glare. Polished metal reflectors directed light. The development of aluminum provided a lightweight and reflective material. Innovations in electrical insulation allowed for safer installations. The development of vulcanized rubber and oil-impregnated paper insulation improved reliability. Connectors evolved into sealed devices operating in humid environments. Social impact and lasting technical legacy. The introduction of effective artificial lighting profoundly transformed urban life. Before widespread street lighting, cities darkened after sunset. Lighting extended the effective daylight hours, allowing economic and social activity to continue. Public safety improved significantly. Well-lit streets discouraged problematic behavior and facilitated policing. Statistical evidence showed reductions in nighttime incidents. Lighting also improved traffic safety for both vehicles and pedestrians. Commerce benefited enormously. Shops stayed open later. Nighttime entertainment flourished with theaters and restaurants. Window display lighting became a marketing tool. Lighting distribution was uneven, with wealthy districts receiving superior service, while poor neighborhoods remained poorly lit, reflecting social inequalities. Cultural changes included altered sleep patterns with lighting, allowing for later work and socialization. Urban aesthetics were transformed, with illuminated streets becoming spectacle spaces. Many engineering principles remain relevant in modern infrastructure. Concepts of network distribution, control automation, and load management laid the foundations for contemporary systems. Modern gas networks use different materials but similar architecture. Some stretches of Victorian pipelines are still in service, a testament to their durability. Electrical distribution has evolved, but fundamental. Principles of centralized generation and local distribution remain. Lighting automation, using timers and sensors, is a direct descendant of Victorian systems. Materials developed for lighting have had broad impacts on the polymer industry, glass technology, and materials science. Preservation of historic systems has become a focus of conservation. Victorian streetlights are recognized as cultural heritage. Some cities operate heritage gas lighting systems in historic districts, keeping the technology alive. Technical challenges. Overcome with ingenuity. Victorian engineers faced technical challenges in developing lighting systems, demonstrating remarkable ingenuity. Purification of coal gas was significant. Raw gas contained corrosive compounds that damaged equipment. The development of multi-stage purification using water scrubbers, tar condensers, and iron oxide boxes represented an advance in chemical engineering, transforming waste into valuable resources. Pressure control in gas networks was critical. Gasometers provided an elegant solution using a floating piston principle to maintain constant pressure. Carbon electrodes in arc lamps exhibited irregular consumption. In DC, the positive electrode consumed twice as fast as the negative, requiring asymmetrical adjustment mechanisms. The development of electrodes impregnated with rare metal salts improved stability, a principle later used in high-intensity discharge lamps. Insulating underground cables in humid environments was challenging. The development of oil-impregnated paper insulation provided an effective solution. Modern high-voltage cables still use variations of this principle. Synchronizing multiple electric generators to operate in parallel required automatic speed governors and synchroscopes, increasing system capacity. Starting arc lamps required higher voltage, demanding starting reactors and a careful understanding of arc electrical characteristics. Solutions developed laid the foundations for modern electrical engineering. If this exploration of sophisticated Victorian engineering and historic infrastructure still in use was fascinating, leave a like now. Subscribe to the channel for more in-depth analyses of historical technologies based on verifiable facts. Click on the video appearing on the screen to continue discovering forgotten innovations. Thank you for watching and for valuing accurate history and technology. See you in the next video.